Now we will be dealing with the first important molecule of phototransduction pathway, that is the rhodopsin. Okay, we will now be dealing with rhodopsin. Now listen, we have already small conversation with respect to rhodopsin, that is rhodopsin is actually a molecule which is made up of both protein part and a chromophore, right? It is made up of both a protein part, right? It is made up of both a protein part called opsin, right, and a chromophore, right? What is chromophore? Chromophore is a substance which gives color to a protein. Clear? Now listen, in case of rhodopsin, the chromophore is known as 11 cis retinal. Clear? Okay, clear? Now a very interesting part you need to understand here is this, that how this retinal, now listen, retinal you already know is an aldehyde, right? It's an aldehyde, right? Now our question is how this aldehyde is incorporated into this molecule or this protein. Okay, now listen with all your attention. You need to understand some basics about this opsin molecule. Okay, now listen, suppose this is the opsin protein. Okay, suppose this is the opsin protein. Now listen, suppose this is your opsin protein. Okay, now suppose this is the N terminal and this is the C terminal. Okay, clear? Okay, so this is the N terminal and this is the C terminal. Okay, now listen with all your attention. So what is the molecular weight of opsin? It is around 30 to 50 kilodalton. Okay, 30 to 50 kilodalton. Now listen with all your attention. You will now find out how many amino acids are there. Okay, clear? Now listen, a very interesting part you need to understand here is this, that suppose this position is very important. You know what is this? This position of the protein is having a lysine molecule. Okay, a lysine molecule. As this is a protein, now listen, as this is a protein, this protein is made up of many amino acids, right? Now in this position lysine molecule is present. Now listen, this position is actually 296th position, that is lysine is the 296th amino acid. So in the 296th position of opsin, lysine is present. Clear? Now listen with all your attention. What is the structure of lysine? What is the structure of lysine? Now listen. So this is actually the structure of lysine. Clear? Now it is very important for you to understand lysine is a basic amino acid, right? Because it has got two amine groups. Okay, one is extra. That's why it is a basic amino acid. It's a basic amino acid, right? Basic amino acid. Clear? It's a basic amino acid. Okay, so this is what? This is lysine. Okay, now listen. So this group is actually the R group of lysine, right, or the side chain, right? So the R group of lysine actually looks like this, right? So this is the R group of our lysine, very beloved lysine, right? Now it is very important for you to understand what happens here. Now listen, we will now be talking about how this opsin is converted into rhodopsin. That means we will have to add in this structure retinal. That's it. Clear? Whether it is 11 cis retinal or all trans retinal, we will talk about that later. But now, right now, we will have to add retinal to this structure. Right? Now listen. You know what is opsin? You know what is opsin? Opsin is a member of G protein coupled receptor. That means it has got heptahelical structure, right? It has got heptahelical structure, right? It has got heptahelical structure. That means suppose this is your, cell membrane. Suppose this is your cell membrane. Don't worry, we will draw this in details when we will be talking about the, visual cycle, okay? So suppose this is your, lipid bipolar, clear? Now, so this is your cell membrane, and suppose this is your G protein coupled receptor, okay? It's a G protein coupled receptor, clear? Okay. Now, this is actually opsin. Now, listen with all your attention. Actually, in some areas like this, here actually there is, retinal present, clear? That means retinal is actually bound to this heptahelical structure. In one of the, loops and turns of this heptahelical structure, retinal is present, clear? Now listen with all your attention. Now we know that this retinal is actually associated with lysine 296, clear? 296 lysine. Now how this occurs? Now listen with all your attention. Now listen with all your attention. You know what is this? You know what is this? This is nothing but 11-cis retinal. This is actually 11-cis retinal. Now why we are talking about this 11-cis retinal? Now listen with all your attention. Where actually the change is occurring. Now listen with all your attention. In this position, the change will occur after light will hit this retinal. Okay, in this position, clear? And this is, that's why is known as 11-cis retinal. This is 11-cis retinal, clear? So a very important part you need to understand here is this. So if this is 11-cis retinal, then how this is conjugated with this lysine, right? Now listen with all your attention. I will be making some changes here, okay? So this is suppose your opsin molecule, okay? Now listen. Suppose this is the lysine molecule, okay? Now it is very important for you to understand. It is very important for you people to understand that what is happening here is very, very important. You know what has happened here? Now listen with all your attention. This is actually the peptide bond. This is actually the peptide bond. Okay? This is actually the peptide bond. Now listen. Now listen. So this is what? This is the structure of lysine. Now a very interesting part you have to understand is this, that this oxygen and this hydrogen will now come out. This oxygen and this hydrogen will now come out. You know what is this happening? Now listen with all your attention. If this hydrogen and oxygen will come out as water, if this hydrogen and oxygen will come out as water, now this will look like this, okay? This whole thing will now look like this, okay? With a positive charge in the over the nitrogen, right? Over the nitrogen, right? Clear? With a positive charge over the nitrogen. Now this thing is nothing but this thing, this whole structure now represents, this whole structure now represents, this whole structure now represents Schiff base. Clear? This is actually the structure of Schiff base. That means what I am trying to say is this, that opsin interacts with 11-cis retinal to form, now listen, this whole thing together with 11-cis retinal, this whole thing is now known as rhodopsin. Clear? Is now known as rhodopsin. Is now known as rhodopsin. Now listen. So when 11-cis retinal interacts with opsin with the help of with the formation of shift base, then this whole compound is now known as rhodopsin. Clear? Am I clear to everyone? Now after this post translational modification, this whole thing will now turn into helix and beta pleated sheets, and this 11-cis retinal will now, suppose this whole protein after post translational modification becomes like this. Okay, suppose this is your this is suppose what, this is your suppose rhodopsin. Now listen, sorry, opsin. Now listen, suppose this is the lysine 296. Now 11-cis retinol is now lying here. Clear? Okay, 11-cis retinol is now lying here. Okay, it is trapped in the molecule of what? Opsin. Okay, it is trapped in the opsin molecule. Clear? Okay. Now a very interesting part you need to understand is this, that how rhodopsin reacts. Now listen, we use rod cells when we are experiencing dim light or we are not experiencing light at all, right? That is, in the absence of light, rod cells will release synaptic vesicles so that ganglion cell becomes excited. Okay, now listen with all your attention. A very important part you need to understand here is this, but when light will fall on rhodopsin will stop working. Rhodopsin will stop working. Why? This is because of the fact that this 11-cis retinal will now be converted into 11-trans retinal. Clear? And in this form of 11-trans retinal, that is the conversion of 11-cis retinal into all-trans retinal, this is actually called retinal or rhodopsin cycle. Clear? Retinal cycle or rhodopsin cycle. Now listen, how this thing changes when light falls on it. Now listen, just the structural basis of how the things changes. Now listen, when light falls, when light photon, light means what? Photon, right? When light photon falls on it. Acha, can you tell me one thing? If I tell you just now, or if I ask you just now that what is the, which theory we are following when we are telling that light photon? Are we actually pressurizing that light is a particle or light is a wave when we are considering light as a photon? Think about that and tell me tomorrow. Clear? And those who are watching, they should also understand what is the basic difference. Okay, when we are considering light as a photon, then what we are considering, light is a wave or light is a particle. Okay, now listen. So this is suppose your light photon. Now listen, when light photon falls on rhodopsin, now listen, when light photon falls on rhodopsin, what changes are occurring? Now listen, actually what is happening is this bond is coming up and this is going down. This hydrogen is going down and this CH3 is coming up. Clear? And due to this transition, this whole part now will, now listen, at first it was like this, okay, but when light falls, then due to the light, this whole thing will become straight. Now what it will look like? Okay, now let me draw this for you, how it will look like. Clear? Now listen, suppose light falls on it, light photon falls on it. Clear? Now suppose light photon now falls on it. Okay, now how this has changed you already noticed, right? So suppose this is your double bond, this is double bond, double bond, double bond, double bond. Clear? Now interesting part you need to understand is this, when light falls, then this CH3 have come up, right, Now listen with all your attention. Actually there was also again NH2. Now listen. Actually this bond was already present, okay? Now listen. Now listen with all your attention. So the Schiff base is remaining in its own place, okay? The Schiff base is not disturbed. Why? Because Schiff base is actually, because of the fact that opsin is now interacting with 11-cis retinal. That means if Schiff base is, broken, then there will be no, rhodopsin present. Why? Because rhodopsin is actually made up of opsin and retinal, right? And this retinal is held in the place in an opsin molecule by this, Schiff base. Clear? Now, interesting part to understand is this. This configuration is called all trans retinal. Clear? This is all trans retinal. That was 11-cis retinal. It is now known as all trans retinal. Clear? Okay. Now, why we are talking about this? We are talking about this because this is actually the chemical basis of your, rhodopsin cycle and all these things. But we will be talking about that in details. Okay, don't worry. Now listen, we will be talking about more physiology here. Okay, right now. A deep insight into rhodopsin is required before we can move on. Okay. Now listen. Suppose this is the cell membrane of your rod cell. Clear? This is the cell membrane of your rod cell. Okay. Now interesting part you need to understand here is this. So this is what? This is actually your disc, right? This is your disc, right? Now a very interesting part you need to understand here is this. Suppose if we can redraw this part at least. So suppose this is the disc membrane, okay? Suppose this is a disc phospholipid bilayer, okay? Suppose this is the disc phospholipid bilayer, okay? Now a very interesting insight is this, that in this phospholipid bilayer, there will be what? There will be what? G protein coupled receptor, that is our beautiful rhodopsin, right? Our beautiful rhodopsin. Clear? So this is actually what? This is your rhodopsin molecule. Clear? This red color is your rhodopsin molecule. Clear? Now listen with all your attention. A very interesting part you need to understand here is this. So this is your what? Disc membrane. Now listen. Suppose this is your, suppose this is your, 11, this is trans or cis. Before the light falls, it will be trans or cis. This is 11 cis retinal. Now listen. Actually, this 11 cis retinal is the place where actually, light photon is coming, right? Now listen. Sorry, this is actually the place where light photon is absorbed. Now listen. Very interesting part is this, that when light photon comes and falls on this 11 cis retinal, what happens is this 11 cis retinal is converted into all trans retinal, right? Is converted into all trans retinal. Clear? It is now straight. Clear? This is now all trans retinal. Okay? All trans retinal. Now listen. Now suppose this portion is actually the suppose this portion of retinal is this part of my hand, okay? Now listen with all your attention. When light is falling, suppose when light is falling, then the double bond now kinks a bit, okay? Kinks a bit. Now this position, due to the change, a small bit of change. Now listen, when light falls, this 11 cis retinal is directly never converted into all trans retinal. there are several steps. Now listen, during these stages of change from 11-cis retinal to all trans retinal, now listen, during these stages from 11-cis retinal to all trans retinal, when conversion of 11-cis retinal into all trans retinal takes place. Now a very interesting part you need to understand is this, that all trans retinal actually cannot be associated with opsin, but all the intermediate structures of 11-cis retinal are always attached with the opsin molecule. Clear? Now suppose this is the this structure, okay, clear? It looks like cyclohexene. Now listen, suppose this is a cyclohexene like structure of this, okay. Now listen, suppose light falls on it, so this is 11-cis retinal. Now the kink is now straightened very little much. Clear? This structure now is called, now listen, this structure now is called, so it was rhodopsin, right? Now when the kinking has just started to straighten, then this structure is now called bathorodopsin. Clear? That means what is bathorodopsin? Bathorodopsin is, suppose this is the original structure of rhodopsin. Clear? And due to the falling of light, the kinking has straightened a bit. Clear? That means the double bond has been straightened a bit. So this structure is called bathorodopsin. That is, this structure, this retinal with opsin is now called bathorodopsin. Clear? Now listen, rhodopsin has an absorption spectra of 500 nanometer. Clear? And bathorodopsin has an absorption spectra of 543 nanometer. Remember this. Clear? Bathorodopsin is now converted into lumirhodopsin. Clear? Now lumirhodopsin has an absorption spectra of 497 nanometer. Clear? That means in lumirhodopsin more straightening has taken place in 11-cis retinal. Okay. Now listen. After lumirhodopsin, what will happen is this: metarodopsin 1 is there. That is, lumirhodopsin is converted into metarodopsin 1. It has a absorption spectra of 480 nanometer. Now metarodopsin 1 is converted into metarodopsin 2. Now this is very, very important. Okay, let me write it. Metarodopsin 2 is really, really important. Now listen with all your attention. Now this metarodopsin 2 is actually very, very important. Why? Because metarodopsin 2 is actually the form of the rhodopsin which initiates the phototransduction pathway or cascade. Clear? Which initiates the light activated step. Clear? That means when rhodopsin is converted into metarodopsin, then only you can expect some results. Clear? Now a very interesting part you need to understand is this, that when metarodopsin is formed, then all trans retinal comes out. All trans retinal comes out, and now listen, all trans retinal will now again be converted into retinol. Clear? Will now again be converted into retinol. Okay. Will now again be converted into retinol. Right? Now listen with all your attention. Now this retinol again will bind with opsin to form rhodopsin in your eyes. Clear? Now listen with all your attention. This stage, that is the conversion of 11 trans retinal into retinol, then the conversion of rhodopsin, right? This is actually this hand of this this hand or this red dotted hand of this flowchart is actually world's visual cycle. This is actually world's visual cycle, which I have taught earlier. This is the importance of Wald's visual cycle. People don't understand that they are two different things, okay? Clear? So these are the things. Now listen, a very interesting point you need to understand is this, that what this meta-rhodopsin is doing. This is really, really important. This is actually really, really important what this meta-rhodopsin is doing, okay? Or sorry, meta-rhodopsin 2 is doing. This 2 is very, very important because there are two meta-rhodopsin, there is 1 and 2, but 2 is more important. Clear? Now listen with all your attention. Why G protein coupled receptors are called G protein coupled receptors? Because they are coupled to G proteins, right? That means, suppose rhodopsin is a G protein coupled receptor, that means there should be a G protein which is also present in this membrane, right? There should also be a G protein which should be present in this membrane, right? Now listen, there is actually a G protein, okay? There is actually a G protein which is present in this membrane. You know what is that? This is called G transducin or GT. Clear? This is G transducin or G transducin. Now listen, GT is divided into 3 subunits: GT alpha, GT beta and GT gamma. Now listen, this GT beta and gamma are associated with each other, and GT alpha actually associates with these two together. Clear? That means, now listen, what will happen is this. This is what? Your extracellular domain. This is the extracellular domain and this is the intracellular domain, right? Now listen with all your attention. What will happen is this. After this rhodopsin has been converted into meta-rhodopsin 2, suppose this is your meta-rhodopsin 2. Now listen. Okay, let me write here. Suppose this is meta-rhodopsin 2. Clear? This is meta-rhodopsin. This is meta-rhodopsin 2. Now listen, meta-rhodopsin 2, actually out of this all rhodopsin forms, that is rhodopsin itself, batho-rhodopsin, lumi-rhodopsin, meta-rhodopsin 1, only meta-rhodopsin 2 can actually activate the G protein. Clear? It's a G protein coupled receptor, right? Rhodopsin is a G protein coupled receptor, but rhodopsin itself cannot activate what? Rhodopsin itself cannot activate the G protein itself or G transducin. G transducin is what? G transducin is a type of what? G protein. It's a type of G protein. Clear? Now listen with all your attention. A very interesting insight is this, that this meta-rhodopsin 2, is the only form of rhodopsin which can activate this G protein. Clear? Which can activate this G protein. That's it. Clear? Now listen with all your attention. When this meta-rhodopsin 2 is activated, suppose this is your, now listen with all your attention. Suppose this is your GT alpha. Clear? And this is what? GT gamma. Okay? And this is GT beta. Now a very interesting part you need to understand is this, that when meta-rhodopsin is activated, okay, then this GDP will come out of this place. That means now this meta-rhodopsin is transferring its energy to this GT alpha, right? Now instead of this GDP, when GDP is coming out, now listen with all your attention. When GDP comes out, then it will be replaced by GTP. Clear? It will be replaced by GTP. Clear? It will be replaced by GTP. Now listen, when this GTP is replaced by GTP, then this GT alpha was forming a covalent bond with its GT gamma subunit, right? Now listen with all your attention. Now listen with all your attention. When this exchange of GTP and GTP takes place, due to the activation of metarhodopsin, what will happen is this. Now, this covalent bonding is now, broken. Clear? Is now broken. And this GT alpha, that is G transducin alpha subunit or transducin alpha subunit, now becomes activated. Is now activated. Clear? Is now activated. It's simple G protein coupled receptor signaling. Okay? GT alpha is activated, just we are using T form, nothing else. It is G alpha, nothing else. Clear? Now what will happen is this GTP bound form of GT alpha or transducin alpha, this will activate a protein. This will activate a protein. Okay? This will activate a protein. Now when G transducin alpha is activated, then what happens is this, that this activated transducin alpha or activated GT alpha will now activate an enzyme known as, phosphodiesterase enzyme isoform 6 or PDE6. Clear? Now listen with all your attention. PDE6 actually looks like this. There are alpha subunits which are catalytic in nature. There is a beta subunit. Now listen, okay, well, wait. There is an alpha subunit. There is a beta subunit. Clear? And there are two inhibitory subunits which inhibits these catalytic domains. There are two inhibitory subunits. Okay, these inhibitory subunits are called gamma. That means PDE6 is a heterotetramer. Listen with all your attention. PDE6 is a heterotetramer. Now listen. These two, that is gamma subunits, are inhibitory in nature. Clear? And these two, alpha and beta, are catalytic in nature. Clear? Now a very interesting part you have to understand is this, that activated G transducin alpha with a GTP molecule now tries to activate these gamma subunits. Now listen with all your attention. Now what happens is this, when GT alpha is activated, then what happens is this, then the gamma subunits are removed. Clear? The gamma subunits are then removed. Clear? The two gamma subunits are then removed. Clear? And alpha and beta subunits are now activated. That means PDE6 activation has taken place. That means PDE6 was phosphodiesterase 6. Okay. Now what do you mean by phosphodiesterase? Now listen with all your attention. What is the role of this phosphodiesterase? Do you know? It will convert cyclic GMP into 5' GMP. Now this is very, very important for you to understand. That this cyclic GMP is converted into 5' GMP. Now listen with all your attention. You know there was a channel that is CNG, cyclic nucleotide gated, right? There was a channel known as CNG channel, right? What is the main important role of this channel? Now listen. Cyclic GMP used to sit here, and this gate will open, right? And this gate will now open, and therefore sodium as well as sometimes calcium will now enter, right? This is what? CNG channel. This is what? CNG channel, right? Now listen with all your attention. When PDE6 is activated, that is when alpha beta catalytic subunits of PDE6 is activated, then what happens is this cyclic GMP will be converted into 5' GMP, right? Therefore there will be a rapid decrease. There will be a rapid decrease in the concentration levels of cyclic GMP. Therefore this channel will now close. This channel will now close. That means now what will happen is this. Suppose this was your minus 40 millivolt mark, this was 0, and this was now listen, what will happen now is this. Due to the closing of this channel, sodium will now not enter the cell. Sodium will now not be able to enter the cell. That means what will happen is this. Now the cell will now listen, the cell will now be in a hyperpolarized state, right? That means its membrane potential will now decrease more and more. That means it will decrease less than minus 40, right? Which is more, minus 70 or minus 40, right? Minus 40 is more. Therefore when sodium channel is closed, or when CNG channel is closed specifically, then what happens is this minus 40 will be reduced to minus 70 or minus 60, like that. Okay, then what happens is this state of this rod cell is called hyperpolarized. This rod cell is now hyperpolarized, and you already know, now you should already know that in a hyperpolarized state no cell can fire, right? Now listen with all your attention. When this cell is in a hyperpolarized state, then what happens is this synaptic vesicle transmission will now release. Now ganglion cell will not be excited. That means when light is hitting rod cell, then synaptic vesicle release stops. Therefore we say that rod cells are important. Now listen with all your attention. Therefore we say rod cells are now very important. Rod cells are very important for dim light vision or when there is no light. Clear? Now there is no space where there is no light. Okay. Now another important question is this: who was actually producing this cyclic GMP, right? The first question you should ask now, after this whole pandemonium has been set, who was actually producing this cyclic GMP? Now listen with all your attention. A very interesting part you need to understand here is this, that this cyclic GMP was actually produced. Now listen with all your attention. This cyclic GMP was actually produced by an enzyme. Okay, the cyclic GMP was actually produced by an enzyme. This cyclic GMP from GTP is produced with the help of an enzyme called guanylate cyclase or guanylyl cyclase. Like adenylyl cyclase converts ATP into cyclic AMP, guanylate cyclase or guanylyl cyclase, guanylate cyclase or guanylyl cyclase will convert GTP into cyclic GMP. Clear? Now listen with all your attention. What is happening here again? Now listen. After the removal of inhibition of PDE6, that is there were gamma subunits, two gamma subunits which are inhibitory in nature, and there are two catalytic subunits which are which when activated will now activate what? Will now activate the conversion of cyclic GMP into 5' GMP. Now listen. These gamma subunits are inactivated. These gamma subunits are inactivated by G transducin alpha, right? Now listen, after the inactivation of after that inactivation of gamma subunits, this G transducin alpha, now listen, this G transducin alpha loses its GTP form or loses its GTP and will gain what? GDP, and will again go to the membrane and will again go to the membrane, clear, and will now associate again with, you know, old friends, right, with G transducin gamma and beta, right? Clear? Okay, clear. Now listen, this whole thing started because of what? Because of this light. Now listen, if you cut off this light, then what will happen? This all trans retinal will again be converted into 11 cis retinal, and all this thing will stop. That means no metarhodopsin will be formed, no GTP will be no GDP, you know, there will be what? There will be GDP, you know, here. Why? Because it has gained GDP and it has gone to its old friends, right? So what is happening here is this is nothing but, you know, a basic signaling molecule, you know, pathway. Clear? So that means in your signaling molecule, what is the basic difference between this signaling and your ordinary signaling, you know, pathway? Now listen, in this signaling there is no ligand, there are only photons of light which are exciting this particular what? 11 cis retinal, right? And 11 cis retinal, when it is getting converted into 11 trans retinal by, you know, bathorodopsin, lumirodopsin, you all know these things. Now listen, this activated G protein now activates what? A G protein, right? Now this activated G protein coupled receptor activates a G protein, and G alpha subunit now gains GTP and activates a protein that is PDE6. Now listen, PDE6 is an PDE6 is a heterotetramer, right? It is made up of 4 subunits, and which are gamma, alpha, beta, and again gamma. Okay, now listen, these gamma subunits are inhibitory in nature, and these alpha beta subunits are catalytic in nature, like protein kinase A. You know, there are C subunit and R subunit. R subunit is regulatory in nature and C subunits are catalytic. You will have to remove the regulatory subunit so that you can activate the C subunit, right? It's like that. Now listen, these gamma subunits are removed actually by this G transducin alpha GTP form. Now after the removal of this gamma subunit, G transducin alpha again goes back to its original form, that is it gains GDP and it loses its GTP form, and again goes back to its, you know, old friends, like, you know, cell signaling. Okay, now this activated alpha beta subunits now converts cyclic GMP into 5' GMP. Okay, therefore due to the decrease in the cyclic GMP concentration, there is no cyclic GMP to sit in this, you know, CNG channel, and therefore the inflow of sodium is reduced, or, you know, inflow of sodium is stopped, and therefore cell becomes hyperpolarized, and due to this hyperpolarization no synaptic vesicle will be released. Clear? And therefore during light, when there is light, your rod cells cannot fire, your rod cells don't fire. We will be talking about, you know, the mechanism of how this thing changes when you are using your color vision. Okay, but not now. This is actually for your dark vision. Okay, this whole thing is for your dark vision. Now listen, in ordinary stage what will happen is this guanylate cyclase actually converts GTP into cyclic GMP, and this cyclic GMP used to sit here, right? Now listen with all your attention. Suppose if you cut off light supply, then what will happen is this whole thing will stop. That means 11 trans retinal will, all trans retinal will be converted into 11 cis retinal, and again it will now be rhodopsin, not metarhodopsin 2. As it is now rhodopsin, that's why it will not activate this, you know, G transducin, that is, you know, a G protein. Then if this G protein is inactivated, then phosphodiesterase 6 will now be inactivated. Therefore cyclic GMP concentration will increase, and therefore it will sit here. Clear? There is no conversion of 5' GMP. There is no conversion of cyclic GMP into 5' GMP because PDE6 is, you know, inhibited in your, you know, dark times. Okay, now very interesting and important question you should have in your mind. Clear? That is, suppose there is PDE6 alpha beta catalytic subunit activation in the cell. So it is, you know, destroying cyclic GMP and it is converting into 5' GMP, right? No problem. There is activated guanylyl cyclase. Suppose there are 100 cyclic GMP. Okay, 100 cyclic GMP has been converted to 100 5' GMP. No problem. There are more GTP in the cell. And guanylate cyclase will continue to produce cyclic GMP, and some or the other cyclic GMP will sit here and will continue the sodium inflow, right? sodium and calcium inflow. Now it is very important for you to understand this doesn't happen. Now a very important question you should understand, that when this whole process, that whenever light is present, then PDE6 is activated and alpha beta subunits will now convert cyclic GMP into 5' GMP, right? Now your question should be how cyclic GMP concentration should be restored, should be back to normal when there is no light, right? Right? Now listen, when there is no light, guanylate cyclase is activated more. Actually what happens is this, guanylate cyclase is controlled by another protein, that is GCAP. Okay, it is called GCAP. It is activated by GCAP. Now what is GCAP? Guanylate cyclase activating protein. Now there are two isoforms of this protein. Clear? Guanylate cyclase activating protein 1 and guanylate cyclase activating protein number 2. Now it is very important for you to understand is this, that whenever light falls here, okay, there is ultimately a drop in sodium as well as a drop in the calcium concentration. Now listen, drop in calcium concentration is actually activating this GCAP protein. Clear? Is actually activating this guanylate cyclase activating protein, and instead guanylate cyclase activating protein is activating guanylate cyclase to work more after light falls on it and it again is now dark. Clear? That means when after the exposure of light, when there is a dark period, then this GCAP is activated, and due to this activated guanylate cyclase will now will be activated more, and therefore cyclic GMP concentration will rise steadily and very fast. Clear? And therefore again cyclic GMP can sit in this CNG and sodium and calcium may enter here. Okay, clear? So this is actually the destruction of cyclic GMP and resynthesis of cyclic GMP, which is actually helping in the dark adaptation by rods. Clear? Okay, thank you.